Hi there, welcome to another video from Hegarty Maths. It's our fourth video on graph transformations. Let's start by what we talked about in the last video. Previously, we had a function f of x and we considered what happened to it if we applied the transformation a multiplied by f of x. Pause the video and double check you can remember what happens to the graph in that case. Well, you should have remembered that if a is a number bigger than 1, then it was a stretch by a factor of a in the y direction. The whole graph was pulled out, stretched in the y direction by a factor of a. And if a was less than 1, but bigger than 0, the squash by a factor of a in the y direction, the whole graph was squashed in by a factor of a. Now in practice, what you had to do in the stretch case, you just had to take all the y values and you had to multiply them by a. In the squash case, all you had to do is take all the y values and divide them by a. Okay? Now in this particular video, we're considering the transformation f of ax. The a now is multiplying with the x. It's not multiplying the function, it's multiplying by the x that you put into the function. Now, I'm guessing now that you can start seeing a pattern. Obviously here we're not affecting the y direction, we're going to affect the x direction, and it's going to be some sort of squash or stretch in the x direction. Let's get the graphing software out to see what's going on. So here we go. Our good old friend graph here, f of x is equal to sine x. That's what we're going to start with. And I'm trying to investigate in this video functions of the form f of ax. Okay, and I'm going to add a slider there. I'm going to start with a being equal to 1. I'm going to say it can go up like that. Now let's look what happens. That's f of x, f of 1x. What happens if I make a 2? See if you can spot what's happening here. How could you describe what's happening there? Let me keep playing and let me show you what's happening. A here is 6.3. How would you describe what's happening to someone here? At the very end, a is 10. To me, it looks like f of 10x meant the graph has squashed in by a factor of 10 in the x direction. So if I let a decrease now, I seem to be stretching out back to what I was before until I get back to f of x. Let's have a look at f of x here. F of 1x. Okay, and what do you think is going to happen if I let a be 0.5, let's say? Well, let's do it. We seem to be stretching out in the x direction here, and in this case we seem to have stretched out by a factor of 2. I'm going to put in some of the key points there. What was 90 across 1 up is now 180 across 1 up. I do seem to have stretched out by a factor of 2 in the x direction. So let me pull it back here so they're on top of each other as they were before. If a is bigger than 1, it seems to be what's happening is we are squashing by that factor. Here a is 3, this is f of 3x. We seem to have squashed by a factor of 3. What was in the original graph 90 across 1 up is now 30 across 1 up. We've divided all the x values by 3. Let me make it all the way to 10 and show you what's happening here. What was 90 across 1 up is now 9 across 1 up, you can see. So f of 10x has divided all the x values by 10. And if I go here to f of 0.5x here, we seem to have doubled all the x values by a factor of 2. So we've stretched it out. So I think we've got enough to go back to our slides and summarize what's happening. So let's go back here and consider a general function and its graph f of x. From the graphing software, we realize that if we try and draw f of ax, where a is some number bigger than 1, then what actually we're doing is we are squashing in the x direction by a factor of a. So we squash in x direction by a factor of a. In practice, what that's going to mean is we are going to take all the x values and we're going to divide them by this number a. And what did it mean when a was less than 1 but bigger than 0? Well, in this case, it actually meant a stretch by a factor of a in the x direction. So this time we're stretching in x direction by a factor of a. So in practice, what that means is we're going to take all the x values and we're going to multiply them by a. Okay? So let's use this information we got from the graphing software in this summary to answer some questions. Pause the video and have a go at this one yourself. So the diagram shows the graph of a function f of x. Sketch on the same diagram the graph of f of 3x. Now what does f of 3x mean in terms of our transformations? Well, we know it's of the form f of ax, and a is bigger than 1, so it's going to be a squash by a factor of 3 in the x direction. So a squash by a factor of 3 in the x direction. Now let's just take some key coordinates and take their x values and divide them by 3. So I'm going to take 0, 0. I'm going to take this one here, which is 90 across 1 up. I'm going to take this one here, which is 180, 0. I'm going to take this one here, which is 270, negative 1. And I'm going to take this one here, which is 360, 0. Now I'm going to divide all the x values by 3, okay, and then plot them with the same y number. So 0 divided by 3 is 0, that stays. 90 divided by 3 is 30, so I'm going to plot 30 with 1. 180 divided by 3 is 60, so I'm going to plot 60 with 0. 270 divided by 3 is 90, so I'm going to plot 90 with negative 1. 360 divided by 3 is 120, so I'm going to put 120 there. Now you can see what's happening here. I'm going to join the dots already with these. You can see that the graph has been squashed by a factor of 3. Now I can continue this on, and I will do. And there we go. That's our attempt at the graph f of 3x. Okay? Right, let's have a go at another one. Pause the video, have a think about this. Well, the diagram shows the graph of the function f of x. Sketch on the same diagram the graph of f of a half x. So we're in the form f of ax here. Because a is less than 1 but bigger than 0, this here is going to be a stretch by a factor of 2. Okay, so we're stretching by a factor of 2 in the x direction. So in practice, that means we're going to take all the x values and we're going to double them. Alright, so let's pick some key coordinates. This is 0, 0. Let's take this one here. This is 90 with 4. This one here is 180 with 0. Let's take this one here. This is 270 across 4 down. And this one here is 360 and 0. Okay, so all I'm going to do is double the x values. So if I double 0, I still get 0. That's there. If I double 90, I get 180. So I'm going to put 180 with 4 there. If I double 180, I get 360. So that's already going to be there. Now you can see what's happening here. I have stretched this out by a factor of 2 in the x direction, and it would end up looking like that. You can imagine this graph there has been totally stretched out by a factor of 2 in the x direction. Okay, last one for you to have a go at. Pause the video, have a go. So in this case, we are given the function f of x drawn for us. We are told it has a minimum point at 3, negative 8. So this here is supposed to represent 3, negative 8, the turning point. It says state the coordinates of the turning point of the following graphs. F of 3x. This, remember, represents a squash by a factor of 3 in the x direction. We are going to divide the x number by 3. So I'm going to divide this 3 by 3, and I'm going to say that its minimum is therefore at 1, negative 8. This one here represents a stretch by a factor of 4 in the x direction. Okay, so if its minimum or turning point was at 3, negative 8, I'm going to multiply this 3 by 4, and I'm going to say that the turning point in this case would be 12, negative 8. And that's it for this particular video. Thanks loads for watching.